All right, so let's start the very good topic called regression with regularization. We're still in the regression session, but this is the last session of supervised regression. So after this topic, we're going to cover a very small topic called feature selection on Wednesday. Then we're going to move to classification, which is the largest section of the whole semester. So in the classification, we're going to expand quite a number of weeks. So we spent only about 3 weeks on regression. Regression is extremely important because you're learning the nuts and the bolts in the end, right? So everything here is the fundamental tools. It's a fundamental two modules, or is you can think about some like different type of nails, different type of hammers, and you can do the combination to make your tools. So you're going to see this repeatedly later. Linear form of representation, nonlinear form of representation, loss function with regularization, different kind of observation functions which you just implemented at the homework, the gradient descent, stochastic gradient descent, or direct analytic solutions will all come later again and again. So here, the supervised regression, as I emphasized many times, this is the simplest setting, so that's why it's easy. So it's much easier to explain about the tools, about the basic forms. So later, you're going to experience harder objective functions, which directly calculate gradient may be hard. If, for example, one of the cases we're going to encounter today. And when in those cases, how do you even do do the optimization? And it gets a little bit harder and harder until kind of a lot harder, but the basics are all here. And so that's why regression is a very fundamental section of the whole machine learning, even though people don't use it a lot, but understand all those deeply can create a very strong foundation for you to understand other more advanced techniques better. And honestly, they're just some kind of revised version of the basic form. All right, so we actually covered optimization, the multivariate linear regression with basis function, and also this kind of encourage us to think about a very important task for the generic machine learning is the model selection, right? So what feed do you pick? Cross-validation. So in the homework 2, you're going to implement the cross-validation. So in the homework 1, we only ask you to implement the training phase. And we don't do validation, we don't do cross-validation, we don't do testing. The only thing we require is just to optimize, feed the data with your model by minimizing the loss function we designed. In our case, just L2, just sum of squared error. And also we ask you to plot that error, the training loss versus the epoch when you have iterative algorithm. And that's a very important figure later, and as no matter how complicated your algorithm will be, that figure, you're always going to use that figure to trying to observe, trying to perform a sanity check. How do my data, how do my algorithm perform on just the feeding task on my current data? Not just to mention the next more important task to generalize well on the testing data. Let's just see how it performed on my current training data. How did it fit on my current training data? So that curvature tells you, give you a very good information. Of course, you can literally, in our case, you can literally just plot the data, then plot the fitted line. But in the high-dimensional case, that's normally not feasible. You just can't plot a hyperplane at all, right? So in the end, that loss curve versus the epoch is a very good sanity checker to help you to observe how your algorithm performs on the feeding stage, Okay, so today we're going to move to, we will revise the loss function from the sum of squared error into something looks pretty odd. It's actually a norm function. So we're going to augment our scoring function with something about the properties of the weight vector we are looking for, just to distinguish what we used to without the regularization phase versus the regularizing phase. Now I'm changing to my theta from the old theta into beta, but they're still just a weight function. So I use beta to represent in the cases when my parameters, when my weight vectors are regularized. So this beta just to kind of distinguish with the previous normal or ordinary cases. So in the cases we don't have the normalized regularization, so this solution is normally called the ordinary least square solution. We just tell you that's the normal least square solution from the normal equation. So today is really augmenting this with the properties on this weight vector, and the properties is constrained through the norm function on the weight vector. So what do I mean norm function? I'm going to review it in the later a few slides. Okay, so again, why do we do this? Two purposes. First purpose is we want to generalize well, because the regularization can help us to perform better on the future data. So this will come more clear in a few future slides, but just keep in mind, why do you want to do the regularization? I want to generalize well. At the same time, some of the regularized solutions give me sparse solutions. And what do I mean sparse solution is it has this has the properties like feature selection, which is one of the regularized solution called lasso. So when you have this model have feature selection properties, and it actually helps the model to be able to explain to the users. And actually, I should also label here, it's also at the same time help the model to be scalable, more scalable to the smaller data, and also more efficient. So all the three properties can be improved through regularization. Yeah, keep that in mind. Okay, so let's review. So the least square solution we summarized, we actually learned before, not the basis function version, just the regular least square regression you implement in your homework. It's called ordinary least square, and it uses a squared loss function, and we can solve it through this normal equation-based analytic solution. And again, so training phase, test phase, and we learn this model, and that whole solution was derived from this sum of squared error. You can just do the derivation, and you've got this solution, and you solve this matrix equation, and then you got the solution is x transpose x inverse x transpose y. Okay, but this whole solution relies on a condition is I actually have to be able to do the inversion of x transposition x. And we actually discussed a little bit about there are certain cases absolutely this is not being able to be inverted. So the most classic situation is when the X is not full rank matrix, and absolutely X transpose X, I should write here, and that matrix in the normal equation, and you just can't. So it's pretty easy to derive this, but let's just first to clarify. So what is the size of X transpose X? many times. We talk about this. What's the size of this matrix? So we know this is the n times p, and because this is transposition, this is p times n. So together, this is a p times p n, a p times p matrix, right? So to be able to do the inversion of this matrix, its rank has to be p, right? Okay, so now we actually know the rank of x transposition times x will be smaller, because this is just a property of matrix multiplication. Its rank will be smaller than, I could write minimal of rank x and rank x transpose. And this is just a property, and this, you can prove it, but we're not going to prove it. So when we know that when x is not full rank, what do I mean x is not full rank? For a matrix n times p, right? Our matrix x is n times p. What is this matrix rank? Largest possible rank. So the rank of this will be the full rank. It's actually when it's full rank is the mean of n p, right? So that's so when p larger than n, what will happen? Oh, sorry, it's p larger than n. So when p larger than n, the rank of x will be smaller than p. And then you just put these two together, the rank x transposition times x will be smaller than p. And of course, this matrix is not invertible. So this is one situation when you have more features than more samples. There's absolutely your x transpose x cannot be inverted. But there are other cases, but this is just a most apparent case. In the real data, actually a lot of cases, you have more features than more samples. And in those situations, be careful. Be very careful, because this is just the most classic case. You can use the regular ordinary least square regularization. Very easy proof. So I have more detailed proofs here, and then I copied those from the notes. So this hopefully can explain a little more detailed, but the proof is all here. All right, so in a lot of cases, you actually cannot use ordinal list regression solutions. And then what should you do? And now let's review a definition called a vector norm. So a vector norm, a norm of a vector, is informally a measure of the length. So especially L2 is exactly the vector length in the Euclidean space. So the definition is actually pretty easy. Honestly, I should change this to Q, because this P might get confused with our exercise P. So this is just whatever Q, so let me change it to Q. Q can be 1, 2, even smaller than that 1. So if when Q equals to 1, we got a norm called L1 norm. The L1 norm is essentially just the summation of absolute values of the elements in the vector. And L2 norm is exactly the length. If you remember the Euclidean distance measure definitions, it's just the square, the sum of square of elements, and then take a square root. And this is exactly that vector length. And there's another norm pretty popular, so maybe, even though we don't talk about it here, it's called L-inf norm. L-inf norm is the max of the absolute values of your elements. Essentially, just whose absolute value is the largest in my vector. I'm using that as my max norm, inf norm. Okay, so in terms of geometrically, because I always try to have a geometric view, L2 norm essentially is this. So if this is your vector, the length of this arrow is your L2 norm. And you can easily prove L2 norm because, again, the trick we always use, L2 norm is equivalent to, because this is the summation of the element sum, right? When it's something of the summation of element sum, it's equivalent to the vector in the product itself, right? We had that trick many times. So this part is exactly x transposition x, and then take a square root. Keep that in mind. It sounds maybe why do I need to understand this, and then it will be very clear in the future slides. So this may be a little bit bad. Yeah. So let me actually got this out. So the L2 norm is taking their square root. Yeah. So the L2 norm is a square root over x transposition x, and if you take quadratic, and then x transposition x equals to the L2 norm square. Just to, yeah, so easily is x. So this is a vector. It all sounds like just a formula change, right? But it's actually pretty important for in a few slides coming to understand the equation in the regularized form. It's this x L2 norms quadratic. Yeah, so keep this in mind. L2 square is my x transposition x. All right, so okay, questions. This is very important. Memorize it. There's have to be a certain level of memorization when we learn this type of, even though it's math heavy, it's all mostly reasoning, right? But there's still a certain level of memorization you have to do. Because this more like letters, and then later you're using letter to build words. If you want to understand those equations like phrase or like English text, think about those equations like an English phrase. If your level of memorization, or there's no memorization at all, every step you're trying to retrieve or trying to search in the books about what are those letters mean, and your understanding speed will be so much slower. And math is just another language. You have to have a certain level of memorization. For English, you need to memorize on the phrase level. Here, you need to understand or memorize in certain levels like this. Okay, I'm pretty sure you'll memorize it now. All right, so let's go on. All the norm function, I guess I still need to use Q. Don't get this P confused with our OP. So this is just a number showing the Q norm. This means the Q norm. Q is a hyperparameter. Q norm, Q equal to 1, Q equal to 2, Q equal to 4. So when you have one norm, just like we said, absolute values, what you get is really just a diamond. So what I'm showing here is the contour map. Hopefully you remember what is surface map versus contour map. Contour map shows the x, and the contour shows fx. On that contour, all the fx has the same values. So this is a contour map. This is the contour map of norm function. So this really shows all the points on the circle has the same 2 norm. And this shows you all the points on this diamonds have the same 1 norm. And this kind of a little weird, some kind of diamond shape, it shows you all the points on that contour has the same 0.5 norm. And you can see there's some kind of pattern there, right? So, and this is the 4 norm. Okay, so now, why do I care about all those? So when we try to motivate about regularization, we talk about ordinal least square solution, which is this. Let's just call that OLS solution. The square solution, you can't do the inversion when the x is not full rank. When it's not invertible, a very classic trick is you just augment the matrix with a lambda I. Lambda I is the diagonal matrix, the I matrix with diagonal 1, and this actually lambda is larger than 0. With this trick, and then you can invert the resulting matrix. This is exactly called regression solution, x transpose x plus lambda I, then take the inversion times x transpose y. But why? Okay, why? What type of loss function is this solution trying to solve? And so there's a little bit, so I have a few slides proof. So trying to prove this is invertible. So if you're interested about understanding something called positive definite matrix, and please feel to read it. And if this is too much for you, feel free to just skip it. So in the end, this plus I trick added on x transpose x makes this matrix positive definite, which is absolutely invertible when lambda is larger than 0. And the proof is actually very, very easy. So I'm going to do very quickly because I think some of you want to understand a little deeper. Okay, so we have x transpose x plus lambda I. I'm going to I want to prove it's positive. So if you remember, a loss function with positive definite matrix as Hessian is guaranteed to have a positive curvature, which is really good to look for the optimal solutions. Then the whole thing we're trying to prove is this form guarantees this to be a positive definite matrix. It's called PD matrix, PD property. But how do you prove PD property is, so I want to prove for any vector, for every whatever vector not equal to 0, A transpose times this matrix larger than 0. And this is the property, this is a definition of positive definite matrix. And this is actually super easy to prove. All right, so now it's the trick I just told you. What is this? I think I'm right. So it's right here. Yeah. So this equals to this, right? So x transposition x, whatever vector transposes itself, this is L2 plus lambda because lambda larger than 0 and A is not a zero matrix. A is not a zero vector, so that's why it has absolutely need to have a certain length, right? This means this is larger than 0. It's guaranteed to larger than 0. And this proves the property of X transpose X plus lambda I to be positive semi-definite. And that's why it's invertible. It's guaranteed to be invertible. So this may be a little bit too much, but hopefully there's some of you like this type of proofs. So this is a more detailed version, and this is a shorter version. And we're going to use this trick again in the later slides. But again, remember, a vector's norm square equivalent to its vector transpose itself. All right, so the whole thing I'm trying to show is I can actually prove this solution is equivalent to, I'm augmenting my scoring function from only the sum of squared error plus a L2 quadratic norm on top of the squaring function. And if your scoring function looks like this is the sum of squared part, right? The summation of y minus predicted x beta. And then you just augment the loss function by adding the beta transpose beta. And then its solution is this. And this is homework 2. You need to prove it. It's actually very easy to do. You just take gradient, set it to 0, and do a few analytic matrix vector multiplication. You're going to prove its solution is the ridge regression solution. Questions? I know sounds kind of scary, but it's actually pretty easy. And always the trick, there's always just a few tricks. Remember that sum of square is a vector transposition itself, and when you're taking gradient, what is the gradient of this form? What's the gradient of the linear beta x, or the gradient of beta transpose x beta? And as long as you know how to take gradient of these 3 different forms, and the solution just come out automatically. All right, so question about this? Okay, but what does this even mean, right? I mean, this all looks like matrix vector multiplication. Let's see is geometric visualization. And to go to the geometric view, we have to turn this view, this is called a Lagrangian form, into this constrained optimization form. So this optimization is equivalent to this optimization. So I'm still performing least square minimization, which is here. And if you do not remember how this related to the sum of square, and this is exactly summation over, this is just the matrix form, j from 1 to n, yj minus beta transposition xj quadratic. So just this part is exactly our sum of squared error. We just write a different form. And we used to write theta transpose x actually is equivalent to x theta, because I think maybe some students got confused. So why sometimes we write like x beta or beta transpose x? So actually beta transpose 1 it's transposition. Yeah, it's the same. So this is n times p, p. This is p times 1. And this gives me n times 1, right? This is actually y predicted vector. If you write as beta transposition, it's 1 times p at x, yeah. You still have to have transposition. Yeah, it's the same as we wrote before. Yeah, it's the same. Yeah. So again, so this is just that 1 minus beta transpose x, and then when you put in the matrix form, then this is the same as we had before. We just now use beta to show it's a regularized solution. Okay, so this plus lambda beta transpose beta is the same solution as summation of beta L2 norm smaller than s quadratic. Okay, so in the end, what is all this even concretely indicate? Okay, so now let's review. We talk about ordinal least square solutions like a bell, right? In this, when you have 2x and 1 j theta, two different theta 0, theta 1, you really have some kind of bow shape, right? So this is the surface map, this is the contour map. In the contour map, you really just go from a random start and then go slowly, a little bit, according to the gradient direction, goes to the center. And that center solution is your, in our case, in this case, we call that beta ordinal least square solution. And this is the contour map if you show in a 3D view and the surface map. So in the surface map, and we actually print out our training error, right? If you think about what is training error, the whole training error is really just this curve. For every theta you calculate that loss. And that loss keeps decreasing until the minimal you reached. And that's exactly that fitting training error versus the epoch you're trying to plot. And this is on the contour map, it just looks, because contour map in the end is the movement of your theta vector. And the surface map is the changes of the objective functions. Questions? You already finished the homework. Hopefully this is very intuitive now. All right, so, okay. So now I have this solution. What does it even mean? I'm adding that beta transpose beta, right? So let's come back to see this. I'm trying to look for a minimal solution with this bow shape of the loss function. At the same time, I want to make sure my beta vector is the summation of that quadratic form is within S quadratic. Okay, so who can tell me what is the contour map of this? Summation of every element and then quadratic is smaller than S quadratic. This is exactly a circle centered at the origin point. And the size of the circle is S. Because every point within the circle satisfies summation of beta I. Let's come back to see this. Is here. The summation of beta, each element's quadratic summation is smaller than S quadratic, which means you can only have solution of those points within the circle. Okay, now I have two goals, right? I want to have on the contour map to be as close as that center, that oval-shaped center, but I need to satisfy the other criterion is the point has to be within this blue circle too. And this is exactly what ridge regression is doing. We have two goals, and we want to satisfy both. And that type of solution is whatever point on the boundary of here, it's almost the, and here hopefully it is at the minimum point it can reach in terms of that bow shape, because the inner, the loss function is lower, right? The outer, the loss function is higher. Of course, this point compared to every point here has a lower loss for that sum of square error loss. I hope this is a little bit clear. Sorry, I put it there, and then hopefully there's another figure like this. So this is the 3D view. So in the end, I have like a bell shape about my sum of error loss. The lower in the bows, in the middle, the smaller of the sum of square error. But at the same time, I have a cylinder constraint. That cylinder constraint constrain all my points has to be within that cylinder. And then this is really just a cylinder, and so there's a cylinder here, and then there's a bowl shape. The higher the loss, the lower, the smaller of the sum of error. There has to be a touch point, right? And that touch point is the solution of ridge regression. It satisfies both. It's within the circle. At the same time, it's compared to all the points in the circle, its loss is the smallest in the sum of squared error loss. Question? Sure.
So you're saying that the solution would be on the intersection between the circle and the other circles?
Yeah, so I can find a perfect cylinder and then a bow shape, and the bow just kind of cut through the cylinder. So the true thing actually is like the bell shape cut through the cylinder, right? If you think about it, because the bow, let me use this, somewhere I can reach, maybe, I think this one I can reach. So yeah, use this. So think about there's a bow, so this is like a bell, this is the lowest point, and then there's a bell go out into the air, and go out in the air, the more far and the higher the loss, right? And then at the same time, you need to have that, you need to guarantee, and every point, if you consider only it's, it has to be within, because this, so for example here, it's, how to say that? So this is the contour map, right? But if you think about 3D shape, it doesn't, it has only the properties of within the circle, and when, so all the points, if I'm coming out, so all the points here, they don't have values, but the constraint is still, so what you're looking for is the x, right? X is a beta, and they just, in the contour, so, okay, again, I think contour map is better, it's easier to explain here. So there's a lot of contour, and the higher the contour far away from that center, so the far away of the contour to the center, the higher of the loss. So in the end, I'm trying to be able to very close in the contour, those contour as close as possible, at the same time within the circle, and then that makes the point, whoever this contour point and touches the S is the solution. And of course, 3D view is there's a loss function out, but this has no loss, so it's a little bit confusing. But yeah, hopefully it explains now. Questions? Sure.
Well, we are basically trying to move towards the center of the contour map, right? Because there is the minimum loss.
Yeah, so this is the ordinary least square solution.
Yeah, but
it doesn't consider the properties of the beta. So the solutions here, they their beta, their L2 norm is larger than S. Again, the solution is I want it to be small, but at the same time, I want the points to be within the S circles. So I have to look for the solution has to be the points within the circle. Every point within the circle satisfy that property, right? Beta transpose beta smaller than S squared. So every point, all the blue points satisfy that properties. Its solution has to be one of these points. And at the same time, I want to minimize the sum of squared error. And if you see the contour map, the more closer to here, the smaller orders of the laws. Of course, there's other loss functions, other contour, look like this, right? And the contour just shows the 3D, actually 2D view of the loss function. And if you compare the solution of this, of course, this is the best solution because this is the closest to this ordinal least square solution. At the same time, it satisfies the circle requirements. And when you have just think about a random, we do equation base or gradient descent base, you can't draw that gradient because the gradient is a little bit shaky. So you need to start from here. Some random points start here because you have to. This is the requirements. Sure?
Because this is not.
Good question. Let's just keep in mind it's S for now. And I'm going to discuss with you what is the relationship of S and lambda in a few slides.
If it's not.
So for now, it's just like the restriction class, like give it.
And there's an analytics relationship of S and lambda. And just keep in mind when you do gradients, in this case, you have to within this circle. And there's no way you move out because that's just requirement. And this is your solution path, speculated. But no matter how you move, you need to within the circle because that's a requirement.
So for this x squared, is there the probability of theta? Is that why we are using this x squared?
This is the constraint you added. Good question. So if this is exactly the point. We are revising the loss function. We are revising the scoring function into something like this. It's not the old sum of square anymore. It's a sum of square plus L2 of the vector you're looking for. I like this. I really like you asking questions because if you have questions, how you like it, there are like 10 more. 10 more, your fellow classmates have the same question. You're helping others. I hope this roughly explains. So even though this is the solution, we motivate you from this invertible the angle, but in fact, the whole thing is we're truly revising is the loss function. And this loss function is equivalent to this form. And this has a good geometric explanation is because if you remember, this is really just this is a circle. This just represents all the points there is within the S-size circle or the sphere in a multidimensional case. And you can only move within the sphere and hopefully find the point has the smallest error, but it's only relative to the sphere points, not relative to all the points.
So the cylinder is lambda beta transpose times beta. Is that right?
Cylinder? Which one?
The circle in the middle, like if you advance.
This one?
That's the blue circle?
Yeah, that's the blue circle.
Okay.
There's a parameter s and
That's related to,
lambda.
Okay.
S is related to lambda.
okay,
I'm going to talk about what's the relationship s and lambda in a few slides, sure?
We only add the extra term when x transpose x is not invertible.
Actually, no. So I motivated the whole thing through one is not invertible. But in fact, ridge regression is a very good solution even if it's invertible. Alright, I think we're pretty. Still questions?
Yeah, the same question, but if let's say the matrix is invertible, in that case means the inverse axis, then in that case we don't have to use this linearization at all.
That's true. So even though I motivate the whole thing through not invertible, but I'm going to show you a few slides. Really, when you add regularization, it has certain shrinking effects. And shrinking effect is good. And I cannot prove it. In general, it's a good solution. It's asymptotically guaranteed. In a lot of conditions, it recovers the best solution. It's a good solution in the end, okay? There's a lot of theorem behind, but remember that, so ridge regression is a very good, stable solution. Okay, so hopefully you understand it, so you search within the circle compared to the previous case, you just search wildly. Alright, so we call this solution as a ridge regression solution, we call this solution as ordinal least square solution. And so, so that's the equation. And this is the 3D view, and I hope next time I can find a better 3D visualization of this. Maybe people do how to use computer animation can help you do that better. But anyway, I hope it delivered the point. So this was trying to show, really, you're not going to do this, you stop here. Really stop at this point in the ridge regression solution. Okay, so what is the effect of this regularization? So I have some proofs here, which is very easy. I'm not going to redo it. It's super easy. So let's assume x transpose x equal to I. When x transpose x equal to I, your beta, the ordinal least square solution becomes what? Becomes x transpose y, right? Let's just assume that. And then because x transposition x equal to I, this becomes I, right? I plus what lambda I becomes 1 plus lambda I. And very easily you can prove in this very special case, beta ridge regression equivalent to 1 over 1 plus lambda, the beta old solution. When lambda equals larger than 0, what does this even mean? When lambda larger than 0, 1 over 1 plus lambda will be smaller than 1. So this means my ridge regression solution is a shrinked version of the original solution. So that's why we normally call this kind of shrinkage regularization. Of course, you can prove other cases if it's not equal to I, but that's just too hard. I'm not going to put it here, but this gives you a rough idea. Yeah, there's even, sure?
Why shrink version is better than the normal case?
Yes, I think I covered in a few slides. But keep that question in mind. So why the ridge regression is better? Of course, we already know better at one case, right? When it's not invertible, this is absolutely solvable, right? That's already one good reason. So now I want to explain some of your question about S versus lambda. I already said, right? This two has the same solution. J theta plus sorry, I still use theta. I should use beta. J beta. Yeah. So arguing J beta plus lambda beta transpose versus J beta and subject to beta transpose beta smaller than S quadratic, you actually can prove. I'm not going to do it. You can actually prove S. So this is the most important, and S quadratic equivalent to summation of beta regressions that quadratic, and you can actually prove S quadratic the proportional to 1/1 plus lambda quadratic. So what does this mean? When lambda large, S small. When lambda small, S large, right? But that's still not very clear, right? When lambda larger than 0, we actually know there's a shrinkage effect, right? 1/1 plus lambda beta OLS. But this is not completely correct. You have to remember I have assumption here. And it's actually much more complicated. And this is just the special case, but you get the idea. All right, so when lambda equal to 0, when lambda equal to 0, what is this? J beta. We are getting the ordinal least square solution. So when lambda equal to 0, and when lambda into infinity, what is it? And beta equal shrink to 0. It's still a little bit hard to understand. So so influence of the regularization parameter. So we already said, and this is S, right? And so when I'm increasing S, I'm increasing this blue circles, right? The blue circle really large. What is it? When blue circle really large. Blue circle so large, it will cover this. Yeah. So that's this. When S got really large, it's equivalent to lambda close to 0, which means there's almost no regularization. Your solution will be the OLS solution. And so this is S really large. And when the lambda goes to infinity, your S is really small, very, very small. S is very small, which means what? Your solution will be very off, actually absolutely off a lot, if your OLS solution is very far from the origin. You penalize a lot. The whole penalization dominant the solution. Question about this?
So if we have do we have any way of knowing the OLS solution is going to be so far? Because the whole point of using the rig is that we don't have a way of calculating the OLS.
So your question is, can I reformulate it? How do you pick lambda?
Well, how do you know if you pick the bad lambda?
Good question. So it's related to how do you pick up lambda. So this is a very important hyperparameter in this type of regularized regression. And it's almost similar to in the polynomial regression, what D do you pick? How flexible do you pick? But in this case, it's about how much regularization you added on the whole solution. Again, I'm going to talk about it. So there's regularization path, but in the end, still people use cross-validation to pick the right lambda. Questions? Yeah. So when lambda is so large, the regularization dominant, and your solution will be pretty off, because very clear from that figure, right? You're not going to go all the path, you're going to stop at the boundary of the circle or the sphere. If S is so large, S is so large, lambda is so small, and the regularization almost has not much influence at all. Okay, so that's the summary, and then let's talk about the next. So I already talked about, like subject to a circle or a sphere. And then you can have all the other variation of shape, right? Why the circle? You can have a diamond. And this is exactly that diamond solution. So rather than summation of beta j quadratic smaller than s quadratic, that's really the sphere or quadratic, the circle geometric representation. Now we're just constrained by summation of the absolute values of the elements smaller than a number. And now we change to absolute value. We talked about it geometrically. This is it. You can actually prove it very easily. So the boundary of that is the L1 norm. The boundary of L1 norm are the lines, all these points. So this gives you a simplex type of shape. And in the 2D case, this is actually just a diamond. And you can actually very easily just B1, beta 1 plus beta 2 equals to that constant S, and this is my boundary, and this is that line, right? And this line, and this line, and this create the boundary plane. And you have to, within this, and then look for the points, minimize the sum of square area, but at the same time considering that the bell shape of the walls, the surface map, and normally there's a good property. So let's just assume, you move here, here, and here. So there's a good property is there's a highly likely good chance this kind of corner shape will touches the corner with your bell surface map. The corner means what? In this case, the corner point means S0, right? This point actually pushes the beta 1 to be 0, and beta 2 has a quantity. So this type of solution will give my beta 1 equal to 0. And when you have a lot of dimensions, it will push quite a number of beta j equals to 0. When you look at your weight vectors, what you learned, and you're going to get your beta lasso will be some kind of vector with a lot of zeros. Some kind of numbers or maybe whatever. So this what we mean it's a sparse vector with certain level of sparsity. Okay, so again, sparse vector because a lot of the entries are 0. Okay, so why is this good? So when you have a lot of coefficients being pushed to 0. And when you perform that y equals to x transposition beta, it's equivalent to I'm moving out, removing a lot of feature out. Essentially, I'm selecting features through the solution by not performing explicit feature selection at all. And I get a simpler model and hopefully a more interpretable model. And this is normally called sparse solution. So this is a lasso solution, this is the ORLS solution. Questions, I hope the ridge regression discussion already resolved all the confusions about 3D. And it's actually very difficult to geometrically show this type of shape. It's easily not this part touches, is the best port position touches that contour. It's normally highly likely it's a lot of corner points touches the contour. And there are a lot of discussion online, feel free to read those. It's about the property of the loss function. Question about this, and I think I don't have a 3D view about this because it's so hard for me to visualize.
In a particular data set, how can we know that whether lasso regression is performing better or ridge regression?
Great question, yeah. So I have a few slides later about this. Yes, so let's compare ridge solution versus a lasso solution versus a ridge solution. So we already talked, right? We already derived. Ridge solution has the shrinkage. It's really shrink, right? This figure almost, I'm shrinking the beta 1 to here. I'm shrinking that beta 2 to here. There's a shrinkage effect, but it doesn't shrink to 0. But lasso is also shrinking, but the shrinking is a little bit different. It shrinking a lot of those beta into 0. One is a soft shrinkage. The lasso is a hard shrinkage. All right.
You can get the same thing with norm of 0.5, right? The same effect.
Good question later. Yeah. All right. So the tuning parameter when you have good tuning parameter on the lasso, you can push some of the coefficient of beta into 0. That has the feature selection functionality. Okay, so especially for this p larger than n case, I mean, you have so many features, even more than the samples. Lasso is a very good choice. It can, it improve the prediction accuracy and also improve the model interpretation ability. Because you actually know what feature is more important because all the other features got pushed out. And but the issue is when p larger than n, lasso can select only up to n variable. It's actually part of the formulation, and I'm not going to prove it. Feel free to read. And the other issue is when you have correlated features. In a lot of real cases, your features are kind of grouping structure, right? This group of features come from maybe one source, that group of features from another source. And this type of features are highly likely to be correlated within the group. But for lasso, it can only select one of the features and then push all the other to 0. So if you think about it, this is really not ideal because you're going to derive a wrong interpretation about who's important or who's less important. So so I already covered implicit feature selection, and why it's good because it's easy to understand, and the other reason is it brings you computationally efficiencies. So this is an example. I'm going to cover it, but in a lot of biology problems, you have more features than the patient samples. So this is a very classic setting less so, it's sparse type of models are kind of dominating approach there. Okay, so I want to talk again why selecting features is good from computational angle, right? We always emphasize there's a math reason, there's also a computational reason. So we had this derivation before. Of course, you actually need to do a little revision. In the ridge case, actually your dominating calculation is this step. This is O cube. Of course, the modern BLAST libraries improve it a little bit, but it's still close to O n cube,